Right, I've just started the recording here. So those of you on the recording, we just start a question. So I can see from the chat we're all in agreement that we have a geometric series here. Okay, so it's geometric. And so with a geometric sequence, we have a common ratio. Now be careful, this common ratio, it might be quite hard to see if you're on phones, for example, but we are going from positive to negative to positive to negative. So we know it has to be negative. And to find that common ratio, we just do the second term divided by the first one, which just gives us -1/2. Okay, you could also do the third term divided by the second one, or the fourth term divided by the third one. It is a common ratio, so it will always be the same. Now our 20th term, we want to use, so the formulae above, this is for arithmetic sequences or series. For the geometric, we want to use AR to the power of n-1. Okay, and I'm glad to see that. I thought perhaps a common mistake might be that you might put the 21st term and instead just accidentally do to the power of 20 rather than to the power of 19 here, but I can't see anyone's fallen into that trap, so that's really good. So we just get -1/512 here. So that is our 20th term. Okay, that's how we find that. Now, the other column here is the sum of the 20 terms. How do we find that? Well, that's what we're going to look at today. Do let me know if you have any questions, chat about what we've done before, but we're going to move on to what we're going to start this week. So we've got the formulae here, and we get this in the given to us in the formula book. So this is given in the formula book, and we're going to prove this in a second because we may be asked to prove it in the exam. So don't just think that just because you're given it in the formula book means you don't need to know where it comes from. You absolutely could be asked to prove this. It has come up. So you may have to prove the sum of the arithmetic series or some of the geometric series. That has come up in exams in the past, more than once. I can't remember which form it's given in the formula book off the top of my head. But either we can do it as a times 1 minus r to the power of n, or in the bracket, the 1 minus r to the power of n bit in the bracket, divided by 1 minus r, or it might be given as the version where you multiply the numerator and denominator by -1. So these two will both give you the same answer. It doesn't really matter which order you use them in, which one you use, just as long as you use either one and you're consistent that you've always got this the right way round. Okay, that is important, that you've got the signs the right way round. So let's go straight ahead and prove it then. Now, yet again, a bit like when we proved the arithmetic series, the proof's not really hard once I show you what you have to do. It's just having that intuition to think of that first step. So I wouldn't, like I said with the arithmetic series, don't learn this line by line, just learn the key step here. So the first thing I do is I'm going to write out the sum of geometric series. So this would just be A plus the second term, AR, plus the third term, which is AR squared. Remember, in the arithmetic series, it's going to go it's AR to the power of n-1. So you've got your first, second, and third terms there. And to go all the way to my penultimate term of AR to the power of n-2. Sorry, it should be n-2. Plus AR to the power of n-1. I'm going to call this equation 1. Equation 2 is going to be almost the same, and hopefully you'll see why I've done this in a second. But I'm just going to multiply every term by r. So I have AR as my first term, because I'm just doing my first term, which is A times by r. AR squared will be my second term, because normally my second term is AR, but times it by r. And then we have AR cubed, and so on, all the way to the penultimate term of AR to the power of n-1 plus AR to the power of n. Can anyone spot, so you might just put this in chat, can anyone spot what might be my next step? Anyone just think what I might want to do next as part of this proof? if we can spot anything that might happen here. Can we see how anything could be cancelled, perhaps? I like the idea of dividing, because we have divided before when we've had kind of simultaneous equations with geometric. So I like the idea of it. The problem with it is you're dividing kind of infinite terms by infinite terms, so you don't necessarily, well, a certain number of terms by a certain number of terms. It's very hard to divide it when it's not just one number that you're dividing by. But I like the idea. I like the idea. Okay, unless I can see anything, it's quite tricky to spot. It's quite tricky to spot. What I'm going to do is I'm going to do equation 1, take away equation 2. Okay, so I'm going to do equation 1, take away equation 2 here. And the reason for that, so this is Sn, take away Rsn. The reason why I'm going to do that is hopefully we can see that if I look at the top line, I've got an AR there and I've got an AR there. So they're going to cancel. The AR squareds are going to cancel. I haven't written it here, but I've also got an AR cubed. It's going to cancel with this AR cubed. The AR to the power of n minus 2, that's also going to cancel with the third term of the sequence the third before last term of the sequence Sn. And also these AR to the power of n minus 1s are going to cancel as well. So all this leaves me with is just simply doing A take away AR to the power of n. Now what I can do is a little bit of factorising. So I can factorise out the Sn. So on the left-hand side, that leaves me with 1 minus r. On the right-hand side, you just get 1 minus r to the power of n. So then what I'm simply going to do is divide both sides by 1 minus r. And then we just get the following. Note that I could have also done equation 2, take away equation 1, and then simply at the end, I just would have had to multiply both top and bottom by -1. In terms of learning this, in terms of revision, remembering this, as I said, don't necessarily just remember this proof line by line. What you really want to remember is the key step, and I'd say this is the key step. Okay, doing Sn take away Rsn. So in terms of your revision, what I would say is, if you're asked to prove this, just simply remember that key step that you need to write out all your terms for Sn, all your terms for Rsn, and then do the first equation, take away the second one. That's the key step that you need to remember here. If you've got any questions, please pop them in chat. Otherwise, we're going to actually go on to use this formula now with a few examples. So now we're going to look at example 7, which is on page 11. But do let us know if you do have any questions. Can't say anything, so I'm going to move on. So first example, find the sum of the first 8 terms of the geometric series 4, 12, 36, 108. So to do that, we need to find A, which is simple enough, that's just 4. We need to find R, the common ratio. It's a geometric series, so it has a common ratio. So do the second term, divide by the first one, and we get 3. And then N is just simply 8. Okay, that's all the information we need to use our formula. And you can use it which way you want. You can use the other version, which is R to the power of n minus 1 over R minus 1. But I'm just going to use it in this form. So simply sub in A as 4. Then we do 3 to the power of 8 here. Just be careful when you're doing this, just to obey the laws of BIDMAS. And we just simply get 13,120. Okay, I know it's 8 terms. You might think it starts off with quite small numbers, but this does get larger and larger at an exponential rate. Okay, it's what we call a divergent series, which is what we'll look at a bit more detail tomorrow. So we'll move on to our next example, example 8. Find the sum of the following: 1024 minus 512 plus 256 minus 128, all the way to a last term of 1. Now, the difference here, we don't actually know how many terms there are. So let's just start off by writing down what we know. We know our first term is 1024, and we can work out our common ratio. Yeah, this is actually the same sequence that I didn't start to at the beginning. It's just going to be minus a half. Okay, doing that second term, divide by the first one, can find us the common ratio. Or you could do third term, take away second term, etc. The problem here is I don't know what n is this time, so I need to ask myself, how many terms does this sequence have? So how many terms are there? And basically what I'm asking is, which term is the number 1? Okay, so those are the questions that you want to think about as you're doing this. So basically I need to find what n is. And I can use the fact that to find any term of the sequence, I just use this formula that we met last Thursday. Okay, to find any term of the sequence, we just do a times r to the power of n minus 1. Now I know this term is just the number 1. I'm looking for that last term there. A is 1024, and I times this by my common ratio of minus a half to the power of n minus 1. Remember, rules of BIDMAS here, we do the indices first and then we do the multiplication. So just make sure you're not just timesing 1024 and minus half together. Make sure that you're dealing with the indices first. Rearranging this, we'll get 1 over 1024 equals minus a half n to the power minus 1. And then at this point, I can simply just switch this in. It might look quite complicated, but remember, what I'm trying to do here is find a missing power. So I can just simply switch this into log form. Just going to give myself a little bit more room to show that. So I just simply switch this from exponential form to log form. So I've got log with my base of minus a half. And I've got there 1 over 1024, and that equals that power of n minus 1. You can just pop that in your calculator. As I said before, if you're not sure how to do this, please do let me know. So work that out. You might even know that 2 to the power of 10, especially maybe if you do computer science, probably, that 2 to the power of 10 is 1024. So this simply will just be 10, but then we need to add the 1, and then we get n equals 11. So now what we can do is actually find the sum. So just use our formula. So use a, write it out again just so we're used to it. Even though it is in the formula book, it's good to familiarize yourself with it. And A is going to be 1024. You've got a common ratio of minus a half to the power of 11, because there's 11 terms in the sequence, and then 1 minus a half here. So you can see here there's a lot of room for error in terms of signs, indices, a lot of things that could go wrong here. So just be very careful that you put this all in correctly, and also when you're using your calculator, take care. Okay, if there's any questions in the chat, please let me know. If not, we'll move on to our final example for today, and then you've got some exam questions to have a go at. Right, so finally, find the least value of n such that the sum of 1 plus 2 plus 4 plus 8, etc. is going to exceed 2 million. It might seem that that's going to take quite a long time to get to 2 million, okay, especially when you start with 1, 2, 4, and 8. But I think you'd be surprised actually how small the answer actually is. Now what we have here is we're looking for a sum to give us 2 million. As I mentioned before, you could set this question up as an inequality here, but I'm just going to set it up as an equation so we don't make a mistake with the sign if we're multiplying by negative numbers. Now, using my formula, what I'm saying here is that 2 million needs to equal a times 1 minus r to the power of n. So a is just 1 here, so I've simply just got 1 minus r to the power of n on top. And on the bottom, I simply just have 1 minus r. So I just have 1 minus 2. So I've got -1 on my denominator, multiply both sides through by -1, and then we're going to, well, I'll just show you that step there. And then what I simply want to do is take 1 from both sides, and then I'm simply just going to multiply both by -1, so I have positives on both sides. You might also want to write this as standard form just to make it simpler. Now I have 2n to the 2n equals 2,000,001. So yet again, I'm trying to find a missing power, which means I need to use logarithms. So just switch this from exponential form into log form. And I should get 20.93. And we really, we don't want to just use trial and error here, especially with a form like this. You don't want to keep just putting in numbers for n. So do use the logs, do it the systematic way. Don't just rely on trial and error here. So the least value of n is 21. Now what you're going to do is have a go at some exam questions, and if you're stuck, what you're going to do is you're going to ask me, Lane or Gavin for help. So just have a go at those questions, and just to kind of recap, make sure that you can tell when it's arithmetic, when it's a geometric series first off, use the formulae, and also you need to know how to prove those formulae. Yes, you do get the sum of a geometric series in the formula booklet, but you do need to learn how to prove it. So go back and have a look at that again if you're not sure. You need a little bit more time to process that, and remember that key step there. But unless any questions, I'm going to stop the recording here. And